Okay, in this video, we're once again transforming graphs. We're talking about the transformations of exponential functions. So let's go through and recall all of our transformation rules. If you add or subtract a value to the x, it works backwards. A plus a number is going to shift it left. Minus a number is going to shift it to the right when you apply it to the x. If you add or subtract a number on the outside, it's either going to shift it up or down. Based on plus, it's going to shift it up. Minus, it's going to be down. A negative on the outside of a function is going to reflect it vertically up and down over the x-axis. If you apply a negative on the inside, it's going to reflect it horizontally or over the y-axis. If you multiply by a number out front, these are stretches, compressions vertically. If the value is smaller than 1, it's going to compress it. If it's a number bigger than 1, it's going to stretch it by that factor. Now it's backwards when it's on the inside. If you multiply the x value by something, if it's a value less than 1, it's going to actually stretch it by a factor of the reciprocal of b. And if it's a value bigger than 1, it's going to compress it by a factor of 1 over b, or the reciprocal of b. So let's go through all of these. Let's do all of our stretches and compressions first, then we'll do flips, and then we'll do all our translations. And this has no stretches. There's no multiplication out front. There's no multiplication to our x value. There's no negatives being multiplied. So therefore, this is all translations. This plus 1 is going to simply translate your graph left 1. I'm just going to draw an arrow. And this minus 3 is simply going to translate your graph down 3. The parent function of this graph, if you were to take away that plus 1 and take away that minus 3 that just transformed it, the parent function here is y equals 2 to the x. Next one, again, if you take away all the transformations, that gives you your parent function. This negative, this minus 5, and this plus 1 is your transformations. So your parent function here is y equals 1/2, all raised to the x power. Now let's go over our transformations. There's no stretches or compressions. There is a flip. It's not inside with the x, so that's going to be a vertical flip. Or that would be a flip across the x-axis. And then the last two things is you simply have some translations. The minus 5 on the x moves your graph right 5. It's always the opposite if it's on the x. The plus 1 at the end is going to move your graph up 1, and that's the graph. And that would be an example of exponential decay, by the way. Your parent function is 1/2 to the x, so that would be a decayed parent function. Take away all of your transformations, and you're left with f of x equals 4 raised to the x power. That's your parent function. Now let's start with all of our stretches. This number 3 right here is what's being multiplied. If you multiply a function times 3, now not the x, here's the x value up here, but we multiplied the whole function times 3. That would be a vertical, since it's times the whole function. Since it's bigger than 1, it'll be a vertical stretch. And that's, since the number is 3, it'd be by a factor of 3. Next up, let's do all of our flips. So the 3 was what stretched it. If you get rid of it, the negative is what's going to flip it. And again, since it is on the outside with that 3, it's not on the inside with that x value, this will also be a vertical flip. And that would be up and down, that'd be across the x-axis. Then your last two transformations will be this minus 2 and minus 7. The minus 2 actually moves it right 2, and the minus 7 moves it down 7. It does exactly what it says it's going to do. Now the minus 2, again, since it's on the x, it works backwards. Okay, next up, 4/3 e to the negative x plus 5. Take away all the transformations, you're left with y equals e to the x. It's an exponential based, natural based function here. So let's do all of our stretches and compressions. There's a 4/3 on the outside of the function, so therefore that's going to be a vertical, since it's on the outside of the function. 4/3 is bigger than 1, so therefore that would be a stretch by a factor of 4/3. Next up, that 4/3 does not have a negative on it. However, the x does have a negative on it. So therefore that negative on the x is going to be a horizontal flip. Again, because it's on the x, that's the reason it's horizontal. And a horizontal would flip it across the y-axis. And the last transformation is going to be the plus 5 on the end, not on the x, so therefore we would move it up 5. Number 5. Have some Let's see, let's start out with our stretches. Got a 5 on the outside, so therefore that would be a vertical because it's on the outside. It'd be a stretch because it's larger than 1, so a vertical stretch by a factor of 5. Next up, we're going to look in front of this parentheses, this negative value inside this function up where the x is at is going to be a horizontal flip, and that would be a flip across the y-axis, left and right. And then finally, our two translations, the -4 is going to move your graph right 4, and the -9 would move your graph down 9. Number 6, we only have two transformations here. Let's start with our stretches and compressions first. Our x value has been multiplied by 4, so that would be a horizontal because it's times the x. Since it's only x, we're going to have to reciprocate that. We're actually going to be multiplying by a factor of 1/4, so that's going to be a horizontal compression because of it being on the x, and that would be by a factor of 1/4. And next up, the only other thing that's happening is the negative out front. Since it's not up with the x, since it's out front, that would be a vertical flip, and that would be a flip across the x-axis. And finally, I didn't identify the parent function, so let's go ahead. That would be y equals 2/3 to the x power. Okay, number 7. Parent function would be y equals e to the x. We got 3 different transformations here. Let's start with all of our stretches and compressions. Up there with the x, I've got a multiplication, so that would be horizontal because it is with the x. I do have to flip the 1/2, so I'm going to get 2, so that's going to be a stretch because 2 is greater than 1 after I flip it. So a horizontal stretch by a factor of 2. Next up, I have a negative out in front of my function, so therefore, since it's not up there with the x, it would be a vertical. And since it's a negative, that's going to flip your function. And the last thing that you've got is the +4 tacked onto the end, which moves your function up 4. The last one of these, your parent function would be 3/4 is the base being raised to the x power. Your transformations, let's start with our stretches first. Stretches or compressions. Since we're multiplying by 3, the x values by 3, it will be a horizontal. You do have to flip it, so the factor is going to be 1/3, so that's going to compress, a horizontal compression by a factor of 1/3. Next up, the flips, you have a negative out front, so since it's not up there with the x, it would be a vertical flip. And finally, the two translations, this will be left 2 and down 1. That's it. Okay, number 9. The next part says graph each function, then identify the key characteristics. Now, I'm going to show you how to graph this, and you don't have to do this way. You could do a t-table, and you could actually plug in stuff and perform all these operations. I'm actually going to graph the parent function, 3 to the x power. I'm going to plug in my values here, and that's what I get. And again, that's my parent function. So what I'm going to do is I'm going to plot those points and see what it looks like. And that's it. Now, I'm going to show you how to actually take that once again and pull some points. We don't have to have all of them, maybe just 2 or 3 of them, -1 1/3, 0 1, and 1 3. That'll be plenty. And let's perform these transformations on it, and let's plot these new points. You only have 2 transformations. Your graph is going to be moved right 1 and down 4. So let's take each of these points and let's move them all right 1. So -1 would move to 0, 0 would move to 1, and 1 would move to 2. We moved all of our points right 1. Now let's move them all down 4. So all my y values, that's how you move it up and down, is on the y value. So let's move all of our y values down 4. So that'd be now at -3 and 2/3. 1 would now be at -3, and 3 would now be at -1. And let's plot those points. Let me scoot over. And there's your new graph. And notice it's identical to the first graph. It's just everything's been moved right 1 and down 4. So our domain of our new graph, notice our domain is anything again, negative to positive infinity. You can raise a number to any power, including fractions, raising it to fraction powers, that's radicals. Our range, notice that our asymptote line got moved down 4 as well. So therefore our range is now from -4 to infinity. Our y-intercept is now right here, and that would be located at 0, -3 2/3. And if we didn't know that, we could actually just plug in 0 for our x value. Our asymptote line, again, is at y equals -4 now because it got moved down 4. This function is constantly increasing, and it is never decreasing. And finally, our end behavior. As we travel to the right on our graph, my y value increases. As we travel to the left on my graph, my y value levels out now at -4. Next up, let's graph this. And since we already know what our parent function is going to look like, this is an example of exponential decay. We know what 1/2 to the x power looks like. We can actually just come up with some values that's on our parent function. 0, 1 would be on there. -1, comma 2 is on there. 1, comma 1/2, and maybe -2, comma 4. So that's plenty of points. Let's take and let's perform now the transformations, and there are 3 of them. My first transformation is I'm going to flip these things across the x-axis. This is a vertical flip, so therefore all my y values, what used to be at 0, 1, gets flipped down here. So a vertical flip simply makes your y value, if it's positive, makes it negative. If it's negative, makes it positive. So let's change all of our y values. And there you go. You can see I simply made my y values the opposite. And then finally, the only other thing that's going to happen is I'm going to move all my points up 2 units. So that means all my y value gets increased by 2, and here's all those new points. And there they are, and I've already put my points on my graph. And notice, again, we know what an exponential function looks like, so I'm just going to connect these dots. My asymptote line, notice we got flipped, so I can see that I'm probably going to level out right there at a y value of 2 because my asymptote line used to be at 0, but this plus 2, I flipped it and moved it up 2, so my asymptote line now should be at y equals 2. So I'm going to go ahead and label that. My domain is still all real numbers. I can plug in anything. However, my range is a little different. We go down forever. However, we have an asymptote line. My graph only goes up to 2. My y-intercept, ironically, didn't change, 0, 1. And again, to find that, we could have also just plugged in 0 right here and worked that out. My increasing interval, my graph always increases from far left to far right, so therefore it never decreases. My end behavior, as we travel to the right on our graph, we level out to our asymptote line, which is a y value of 2, so we approach 2 on our y. As we go to the left, we go down forever to negative infinity. Our next problem. Now, again, another way of graphing this is you could just do you a t-table. So we can try it this way just to show you every method that we have of graphing. Just plug in some x values to find some y values. Now I would be careful what I plug in for x so that you don't want to plug in something like 3 or 4 because that would make your exponent get really large. I know when I plug in -5 it gives me 0, so what I'm going to do is I'm going to plug in some points around -5, maybe right there. And when I plug those in, I'm just going to plug in 1 for you. Plug in -7, you now have 3 times 1/4. When you do -7 plus 5, it gives you -2. To raise a fraction to a negative, you flip it and make it positive. So that'd be 3 times 16, which is 48, which I don't think is going to fit on my graph. Now let's go ahead and do the exact same thing to the rest of these and see what we get. And there's my points, and there's a sketch of my graph. And notice what transformations happen here. We had it is an exponential decay, and it got stretched vertically, so that's the reason it's taller. And in addition to that, it got moved to the left 5. So there's why it ended up looking the way that it did. Our domain here will still be all real numbers. Again, exponential functions do not have domain restrictions. Your range values, again, it looks like you have an asymptote line at 0. That thing levels out, so therefore it'd be 0 to infinity would be your range. Your y-intercept, Now this one's going to be tough because we can't tell where it crosses the y-axis. So to find our y-intercept, we're going to come over here and we are going to put 0 in for our x value. So that gives me 3 times 1/4. 0 plus 5 would be 5. So 3 times 1/4 to the 5th power. That'd be 3 times 1 over 1,024, which would be 3 over 1,024. Rather small there, y-intercept. 0 comma 3 over 1,024. Nearly crosses at the y-axis. Increasing interval, notice that this function is decreasing forever, so therefore it is never increasing. And finally, our end behavior. As we travel to the right on our graph levels out to our y-intercept. As we travel to the left, my graph increases without bounds. So we go to positive infinity. Next graph. E to the negative x plus 3. Again, we could take and I believe that's what I'm going to do. I'm going to take my parent function. I'm going to perform, there's only 2 basic transformations here. We're going to flip our point across the y-axis, flip it horizontally, and then move it up 3. So here's some points that are on your original function. And again, that parent function that I pulled these from was y equals e to the x. Now this one has been flipped. Again, it's been flipped horizontally. So that means that it got flipped across this y-axis. So that means your x value changes signs. So let's go ahead and change all the signs of our x values. And that's what happens there. And then finally, the plus 3 is going to take all my y values and simply move them up 3. So that'd be a 4, a 5.7, and a 3.4. Now, since we are moving our function up 3 units, remember that we are also moving our asymptote line as well. So our new function is going to cross at 0, 4. Negative 1, 5.7 is going to be somewhere right in there. And 1, 3.4, 1, 2, 3 is somewhere right in there. And again, I told you our asymptote line also got moved up 3 units. So we know that our asymptote line, and I'm going to go ahead and write it down, is going to be at y equals 3. Let's draw our graph. And there is my function. My domain is going to be, again, all real numbers. My range is going to be from the asymptote line up. My y-intercept also got moved up 3 units, so it is now located at 0, 4. Increasing interval, this function never increases. However, it decreases everywhere. And finally, our end behavior. As we travel to the right on my graph, again, it levels out. My y value does, levels out to the asymptote line. As we travel to the left, my y value increases without stopping. Next function. Again, your parent function is negative, or is 1/3 to the x power. You can use it. Or again, I'm just going to do me a table of values to graph this. X and y, and we're just going to plug in some values that, let's look at our exponent here and try to find some good things to plug in. When I plug in 1, that's going to give me an exponent of 0. So I'm going to put that in the middle. Then I'm going to plug in values on each side, maybe 0 and -1, and then 2 and 3 on the other side. I'm going to go ahead and plug in a couple of them for you. Let's go ahead and start with -1. When I plug in -1, my exponent is now 2 times -2 or -4. So that'd be -1/3 to the -4 power. The negative stays. You're going to flip your fraction and make it a +4. Make sure you do your exponent first. This will be the negative of 3 to the 4th, which is 81. When you plug in 0, your exponent is now 2 times -1, which is -2. That's going to be the negative of, let's flip our fraction and change it to a +2, and that would be a -9. When I plug in 1, that changes your exponent to 2 times 0, which is 0. You don't have to flip anymore because 1/3, anything to the 0 power will be 1. So you have -1 now. Next up, you have 2. So plug in 2. That'd be 2 minus 1 is here. It'd be 1. 2 times 1 is 2. So it'd be negative of 1/3 squared would be 1/9. And then finally, when we plug in 3, that'd be 3 minus 1 is 2. 2 times 2 is 4. So that's going to be the negative of 1/3 to the 4th, which is 1/81. Now let's take and plot those points. And there is now your function. Now let's look at, would there be anything that changes our asymptote line here? Notice that we're not moving this function up or down. We flipped it vertically, which is the reason it's down here. We moved it to the right one. We stretched it, or actually compressed it horizontally by a factor of 1/2, but nothing to change our asymptote line. So the asymptote line is still going to be at y equals 0. And the reason I did it first is it's so important to do that so that we know about our range. Now our domain, still the same, all real numbers, but our range is going to be negative infinity up to that asymptote line, up to 0. Our y-intercept, we did have over here on our graph, it's going to be at 0, -9. Anytime your x value is 0, that's your y-intercept. Your function increases forever in both directions, or from left to right, so therefore it does not decrease. And then finally, our end behavior. As we travel to the right on our graph approaches our asymptote line, and as we travel to the left on our graph, it goes down forever. And the next one, we're graphing e raised to the 1/3 x plus 2 power -1. So we have a couple of transformations that are just translations, and then we have this 1/3 that's going to either stretch or compress. So let's go ahead and we'll try to work this with our parent function. So let's identify a few points off our parent function. And now let's perform our transformations. Again, we always start with our stretches, compressions here. This is a horizontal. Okay, since it's horizontal, we're going to have to reciprocate this. We're going to have to flip it, and we're going to get a factor of 3/1. So that's going to stretch it horizontally. When I'm talking horizontal, is we're going to take our x values, and we're simply going to take all of our x values and stretch them times 3, or just multiply them by 3. And there's our 3 new points. Now the next thing and the last thing we're going to do is we're going to take both our x and y values. We're going to move our x values left 2. Let's go ahead and do that first. Take all 3 of your x values, move them left 2. And we're going to take all of our y values and move them down 1. So 0.4 is now going to be at -0.6. 1 is now at 0, and 2.7 is now at 1.7. And let's plot those points and see what our graph looks like. And there it is. Notice again, it got stretched horizontally and got moved left 2 and down 1. So since it did get moved down 1, that is going to change my asymptote line to y equals -1. My domain is still all real numbers. My range, however, since my graph went down 1, my range is now from -1 to infinity. My y-intercept is now, well, it looks like it might not have changed. It looks like it's 0, 1, but to know for sure, again, we're going to plug in our 0 for our x value, and we're going to see what we get. We're going to find f of 0. So let's take our original graph, original function. F of 0 is going to be e to the, 0 plus 2 will be 2. 1/3 times 2 will be 2/3 minus 1. When you plug that into your calculator, you actually get a value of about 0.95. So it looked like it was at 1, but it wasn't quite at 1. So 0.95. Our increasing interval, it increases everywhere. So that means it never decreases. And our end behavior, as we travel to the right on our graph, my y value increases. As we travel to the left on our graph, our y value levels out to the asymptote line, which was -1.